bond dipoles of a molecule's bonds can lead to a molecule having a permanent dipole moment. Let's look at hydrogen fluoride. Because fluorine is more electronegative, there is a partial negative charge that resides on the fluorine and a partial positive charge that resides on the hydrogen. What we mean by this is that the shared electrons between these two atoms we can think of as spending more time around the fluorine than the hydrogen. That's all we're showing there. We can represent this another way with this arrow type notation, where the arrow points towards the more electronegative element. That is, it points in the direction that the electrons are going to spend more time. And then on the other end, you can almost imagine this as being a little positive symbol for a partial positive charge. Another molecule that has a permanent dipole moment is water. Oxygen is more electronegative than hydrogen, so there is a partial negative charge that resides on the oxygen and partial positive charges that reside on the hydrogens. For our purposes, we don't need to quantify those partial charges. We just need to know that they exist. Using the arrows, we can represent the bond dipoles this way. In other words, we need an arrow for every bond, and there are two bonds here. The arrow points towards the more electronegative atom in each case. HF and water both have permanent dipole moments, and what that means is they are polar molecules. Polar molecules tend to align themselves with each other and with ions. If we take hydrogen fluoride again and show a bunch of other hydrogen fluoride molecules, they tend to align themselves in this way, where the fluorines from one molecule want to get together almost with the hydrogens of other molecules. And this is particularly noticeable if we cool this substance down. In other words, the partial positives of one molecule tend to connect or be attracted to the partial negatives of a different molecule. In the same way, if we were to somehow react or mix HF with maybe ammonium nitrate, and this is just a hypothetical example, but you can see here that the negative nitrate ion would tend to get together with the H because it's got a partial positive charge. The ammonium ion, being positive, would tend to want to be close to the partial negative charge on the fluorine. Now here's a nomenclature tip. For binary compounds, the less electronegative element always comes first. For example, HF is called hydrogen fluoride. We're talking about the compound here, not when HF has been bubbled into water, in which case it becomes hydrofluoric acid. Hydrogen is less electronegative and the fluorine is more electronegative, so the less electronegative element comes first. Sulfur dioxide, sulfur is less electronegative and oxygen is more electronegative. Compounds of metals with high oxidation numbers, like 4+ or higher, tend to be molecular rather than ionic. In other words, they tend to act kind of like covalent substances, even though they're metal, non-metal compounds. For example, if we take these three compounds, we could figure out the charge on each of the metal ions. In the first case, 4+. In the second, 4+. And in the third case, 7+. In each of these cases, that is when metal ions have an oxidation number of 4+, 5+, 6+, 7+, those compounds, and here are three examples down here, they tend to behave kind of more like covalent or molecular compounds rather than ionic compounds.